So in this video, we're going to do two things. Thing number one is we're going to review Newton's method for finding the roots of a function, and then we're going to review we're going to present a multivariate version for Newton's method that finds the point at which a nonlinear system of equations is zero. So let's look again at what we were doing with Newton's method. The whole thing started from the application of the Taylor series, right? So let's imagine that we have a function f of x. X is the input, the independent variable. F of x is the output or the dependent variable. And let's say there's a function here. It's drawn sort of like a quadratic that represents f of x. Well, another way that we can write this function is through the application of Taylor series. So let's say we are in possession of knowledge of f of x, f prime of x, f double prime of x, and so on. Then we can estimate the value at some displacement from x, right? So at some x plus some h. And we can estimate this by a linear combination of the value of the function, the value of the first derivative of the function, the value of the second derivative of the function, all of these evaluated at point x, right? And the farther, if we choose a small h, we just multiply h by these derivatives, and we should get an approximated version for the function. And the more terms we take on the series, the closer and closer our approximation will get to the actual function. So the whole idea behind finding the roots is to find where this function f of x equals 0, right? So we are searching for the roots, and so we would like to find some value of x or some x plus h where this is 0. This is what we're trying to solve. So we don't know what this h should be to displace us from the point x that make this 0. However, note that if we take only these two first terms of this equation and ignore the other ones, so we'll make an error, but this is going to be a linear function on h, and we can certainly solve for where, which value of h will make this function cross 0. So let's do that. So we're going to write that f of x plus h is 0, so 0 should be equal to f of x plus h f prime of x. And once plus, we're going to make an error because we ignored this term. So, but I'm not going to write this error. I'm going to imagine that this is a good enough approximation that I don't have to worry about the error right at this minute. Right? So, and again, remember that we assume that we're in possession of the value of f of x and the value of f prime of x. And what we don't know is the value of h that will make this right-hand side equal to the left-hand side, which we set to 0. Because we set this to 0, and this is a linear function on h, we can simply solve for h now. So we subtract f of x from both sides and divide by f prime of x, right? Really simple. So our value of h will be minus f of x divided by f prime of x. So now we make a few substitutions, and we're going to imagine that we have an iterative value, an iterative procedure where we start, let's say we start with some value of x. We call this x1, right? And this will represent our initial guess. We would like to produce x2 that is an update of this guess, which will be equal to x1 plus the h. Which h? The h we just solved. So we plug in for x here, we plug in fx1. So our h will be, our x2 will be x1 plus h, which will be minus f evaluated x1 divided by f prime of x1. Once we have this x2, we compute x3, which will be the same application of this idea, will be x2, x2 minus f of x2 divided by f prime of x2, and so on. So the Newton's method formulation here that we can apply is the following formula, which we derived in our past video, which says that our xi plus 1 will be equal to xi minus f of xi divided by f prime of xi. Right? This all I did here is substitute, I for 1 here in this case, and I for 2, and you can see xi plus 1, right? So it's, if this is 2, this I plus 1 becomes 3. And so this is the general way to write this formula. And graphically, what's happening here with these formulas is we start, let's say, with some value x1. Let's say this is our initial guess. We evaluate f of x1, which in this case may be somewhere around here, and this is f of x1. F of x1. Then we use the first order Taylor series, or first order meaning one term only approximation, one term on h, so 2 terms here, more precisely speaking, to approximate what the slope, what the line is that has the same slope at this point as the function. So this is going to be our line, and I'll try to draw a line here that passes through that. Right? More or less is that. So here's our line, and this is going to be our function that it's a function of y equals f of x plus h f prime of x. Right? And we ask, where did this function cross 0? And this will be here, and we solve for that. So this is going to be our x2. We then repeat this process. Okay, x2 is my new guess now, and I evaluate f of x2. And I repeat this process. I draw another line. Oops, that's not what I wanted to do. I draw another line that has the same slope as in that point. I repeat the process, and I ask, where did this line cross 0? And it was here, so I call this x3. And you can see with very few iterations, if we start with a decent guess, with very iterations, I can get very quickly to the actual root of this equation, which would be more or less here somewhere. So by 3 iterations, I already got very close. So this is the graphical representation of the application of the Taylor series to solve for the root. This is known as Newton's method. Throughout this course and other courses, you'll see Newton's method you'll see many methods, numerical methods, being called Newton's method, because Newton did many things, including this method for finding roots. So the point here now is let's look at a multivariate version of Newton's method. Okay, first of all, what does it mean? What do we mean by multivariate? We're going to now solve a system of nonlinear equations. And here's an example system that I've written down. So let's put this here. So let's say x squared plus x times y equals 10. And let's say y plus 3xy squared equals 57. So we have here now two equations, 1 and 2, and two unknowns, x and y. However, unlike our linear system of equations, the unknowns appear non-linearly. This is a non-linear function on x, for example. X squared is not linear. Right? Y also appears non-linearly here. So we can't use that theory of matrix vector multiplication, Gaussian elimination, inverse of a matrix, and so on. Not in the same way, at least. So how do we solve this non-linear system of equations? Again, we will apply the same technique as we did here. We'll start with an approximation for our function. Will be a multivariate Taylor series. We'll take only the linear terms. So we'll approximate, we'll have a multivariate, let's say quadratic function or some other nonlinear function. We'll approximate it with a plane, some hyperplane. And then because we have a linear approximation, we'll end up with a linear system of equations. We solve for where that linear system equation crosses zero, and we'll continue, right? One question that you may ask, well, what do you mean crosses zero? We have something, it has to cross some other point here, not zero. Well, it's very simple to essentially just take this and rewrite this by moving this 10 to the side, right? So subtract 10 from both sides and subtract 57 from both sides of this equation. So we rewrite the system as x squared plus xy minus 10 equals 0, and y plus 3xy squared minus 57 equals 0. So now it's like we're back to the same problem. We would like to find the value of x and y, so that I plug into both of these equations and I end up with 0. So it's like finding the multivariate roots of an equation. And this equation is also multivariate. There are two equations and two unknowns. But otherwise, we're back to the same thing. And we may even write, sometimes we write these two equations here. Let me do one more simplification. We call this, call this capital F1 of xy, which again is x squared plus xy minus 10. And F2, big F2, is xy equals y plus 3xy squared minus 57. And again, we would like to find the value x and y, so that makes F1 to be 0 and F2 to be 0 as well. So our whole goal can be stated: find the values of x and y that make this function F1 to be 0 and function x2 to be 0 simultaneously, right? And this is what you mean by the multivariate roots of an equation. So we're going to apply the same technique that we did here. So now we need to find out what is a good form for a multivariate version of the Taylor series. And we're not going to derive this here, but we're just going to use it. We'll state that the multivariate Taylor series is given by, now I'm going to call this, let's call this this vector f. So let's first write this vector x, right? So x will be, I'll refer to this vector x as simultaneously the coordinate little xy, right? So these two coordinates, x and y, I'm going to assemble them into one vector, and I'll call this vector x. Note that I drew a bar over x, as we decided earlier on in the course that we're going to do for vectors. And we're going to write these two values and put them in a put them in a vector as well. So let's call this a little f vector, which is a function of our input vector, to be f1 of xy, f2 of xy, right? So I'm just stacking them and calling them vectors, just so that I can use the multivariate definition of the Taylor series. And the multivariate definition is pretty much the same thing as the univariate, but now everything is a vector. So we ask, if we know the values for this function, f of x, and we know the derivatives of this multivariate function, we'll have to talk about that, what that means in a second. But then we can write this as in the following form. This will be very similar to what we had before, f of x, plus, now this matrix, which I'll write J for Jacobian, of f evaluated at x. I'll talk about what this means in a second. So this is going to be now a matrix times our vector h, right? H is once again that displacement, that which in principle at first sight is unknown. We would like to solve, right? We're going to be given the value of the function evaluated at the vector x and the derivatives of the function assembled in this matrix evaluated at x as well. And we seek the h that makes this whole function here on this side 0, right? And just like before, we're going to take only the first two terms. So, but I just want to write an acknowledgement that we're making an error, and this error would be, roughly speaking, of the order of this vector h multiplied by itself, right? So when you multiply a vector by itself, you first transpose it like this, and then multiply these two things together. So we're going to make an error, and the error will be order of h squared, but now h is a vector, so it's h transpose h. And like before, right, we took, in this case here, we took these two terms only as an approximation here, and we set these other ones, imagine that they were 0. We're going to do the same thing here. So here we're going to call, we're going to throw away this guy, right? And we're going to imagine that f of x plus h will be equal to just f of x plus j f of x times our h. And right, and once again, we're trying to solve for the h that displaces my original x so that this is 0. So let's pause here and try to understand what this matrix J of f here is. This is known as the Jacobian matrix. In this example, this will be a 2 by 2 matrix, 2 rows and 2 columns. And the Jacobian is simply a collection of all the derivatives. But now we have 2 derivatives to worry about, right? In fact, 4. So J of f of x, in this case, will be a matrix where we have df1 xy dx. The second value of this matrix is df1 xy, and you guessed it, dy. Here on this entry we have df2 xy dx and df2 xy dy. And this is our Jacobian matrix. Note that we needed to have this kind of extended definition of a derivative, right? Where the derivative is a concept for a univariate function, a function of one variable, of one independent variable. Now we're looking at a function, it's a vector function, right? Which really is a function of 2 independent variables, so there are 2 equations here. So we can differentiate this first equation by the first variable, and that's over here. And we can differentiate this first equation by the second variable, and that's over here. And we can separate the second equation by the first variable, that's here. And second equation by the second variable, that's here. And that's the collection of all possible derivatives that I can have of this multivariate function over here. And this is, here is the multivariate version of the Taylor series, right? There is another term here, the quadratic term. Actually, there is the Hessian matrix of these derivatives. And we're not going to get into that because Newton's method, the multivariate version, doesn't require these other ones. It assumes that this term is a very small error that you're committing. And so once we have this, then we set this to 0, right? And again, once again, we imagine that we know the value of the function at some x, which some x will be our initial guess, and we know the derivatives of the function at that value x. We're searching for the h that will make this equation, which is an equation for let's say a plane in multiple dimensions, in this case in 2 dimensions. We search for the h that will make this 0. So we set to 0, we subtract the vector f from both sides. So let's do that. So we're taking this equation now and rewriting. So this is going to be f of x plus the Jacobian f of x times h, and that has to be 0. So we're going to subtract this from both sides and say that j of f of x times h equals f of x. And once again, this is known. This is known. And this one is unknown. We are searching for the h that makes this equation correct, that solves this equation. How do we solve this? Well, now we have a linear system of equations. Now this is a linear system because these guys are known. This matrix will be given to you. This vector is also known, will be given by, you know, the function evaluated at the initial guess and the derivatives of the function evaluated at the initial guess. This is unknown. So we can solve this with, for example, Gaussian elimination. Right? Which is something we covered for linear systems of equations a while back. MATLAB has a function that you can just plug in and play. So does Python. Or we can also write as h being equal to the inverse of this matrix, which is another concept that we studied earlier on, right? A 2x2 matrix that whose determinant is not 0 will have an inverse times f of x. And here is where we do the same thing before, right? Remember, we derived this based on the Taylor series over here, right? And we derived a very similar thing, right? H was f divided by the first derivative of f, negative, right? So here, once again, oops, I forgot a negative over here, right? So when we moved this guy to this side, I should have put a negative in front of the f. So this should have been a negative, all negative here. Right, now we have this f here, which is a vector, and we're not dividing by, we're not just dividing by the first derivative, right? Because we don't have one first derivative, we have a matrix of first derivatives. So we take the matrix inverse, which is the equivalent of division for multiple variables, right? But what I was going to say is that we do the same thing here. Remember, we turn this into an iterative equation by replacing, essentially, we said here that, you know, that xi plus 1 equals xi plus h. And this is coming, for example, from here, right? Or any of the other iterations. So we can say that h equals xi plus 1 minus xi. That was for the univariate, in case these unknowns were just single values and not vectors. But now down here, as you'll note, we have vectors. So we can call x to be our x1 or xi to be our initial guess. And call h again, our vector, to be xi plus 1 minus xi. All of these are vectors, by the way. Right, so once again, we can rearrange this and write this as yeah, I mean, it's the same thing, right? So so we're going to take this and plug it in over here in our equation, so x is our initial guess, so we're going to write that xi plus 1 minus xi equals minus the inverse of the Jacobian f of x at xi times the vector f at xi. Right, so once again we can take this, subtract xi from both sides, where we can write xi plus 1. My new version for the two values, now we're solving a 2x2 system of equations, right? These are nonlinear equations. Here's the example we started from, for example. And so our solution here will be, the iterative solution, just like before, will be minus 1 f xi. Right, so this is the derivation for the multivariate version of the Newton's method. So let's take a look and let's apply this to an example. So let's solve this exact example here, where we have our vector. So let me state this again because it's kind of up there, right? So we have this equation of f1 of xy will be x squared plus xy minus 10. And once again, we're setting this to 0, right? So it's like finding the roots. And f2 of xy equals y plus 3xy squared minus 57 equals 0. Right? So this will be the example that we'll solve in the next video.